Hi there, this is an Italian high school teacher speaking, but this lesson is addressed in English for a reason I will explain later. The sound, the audio is not that good, so better use earphones and you get a more accurate sound. Well, the issue we are discussing in this video lecture is briefly identified by SDC. What does it mean by SDC? Means supersonic drag coefficient. It's a very specific topic, which is the last one in a long set of video lectures about sound, waves, and speed of sound also. Why in English? Well, drag coefficient. My father was an engineer, an aeronautical engineer, and she used to tell me a lot of things about airplanes, so things like that. And I remember once I asked about the reason of the name sound barrier. In Italian we say the wall of sound, the sound barrier. What kind of barrier is? And he explained me very quickly, just drawing a plot like this and saying this is Mach 1, this is the speed, velocity, and this is the drag coefficient, CD, coefficient of drag, also known as CX, because it's the coefficient in the x direction, in the movement direction. And he told me simply that the drag coefficient was almost constant up to Mach 1, then increased almost 3 times, just to decrease after that. And he was, yes, that was not a very accurate information. There was no function, or was a simple consideration, and that explained rather reasonably that something strong takes place when you reach Mach 1. And after that, this kind of coefficient decreases, and so you got less problems, less obstacles to overtake after that. The critical situation is Mach 1. And graphically, if you consider those famous drawings, those sketches showing how the sound waves behave when the airplane reaches Mach 1, it's reasonably correct that when you are over Mach 1, there's not such an accumulation of waves. It seems a more or less easier situation. And this is, let's say, shown clearly by the experimental data. That was in the 70s, many decades ago. Few months ago, reading about Concorde flights made just a few years before it was grounded in 2003 or 4. There are many. If you search on the web with these words, Concorde, afterburner, you find here and there many sentences talking about the fact that Concorde pilots had to turn the afterburner on just to overtake, to get over above Mach 1, and then it was there was no need, and that's a good thing, because with the afterburner on, the fuel consumption is extremely high, and that matches more or less with this fact. My father told me that the drag coefficient drops after Mach 1, so you don't need so much power. Okay. Recently, when I was arranging a set of video lectures, in Italian of course, regarding the speed of sound, I just found on the web a very accurate graph regarding this situation, which is, well, actually months ago, maybe a couple of years, I found a graph like this, which is not so accurate, and it might be that no citations. It might be a sort of Excel plot arranged using some data, maybe even approximate or invented. But in the end, and that is the reason why this video lecture is in English, I found on blog named Math Science Notes, I guess .com, not sure, but anyway, you can find it very easily. In such a blog, there was a very accurate plot of this situation regarding an artillery shell, not an airplane, but anyway, a plot where the very several dots were appear to be derived from real data regarding that artillery shell, G7 projectile. That made me guess that this sector, this part of the diagram, was a sort of K over V. I mean, a hyperbole, the simple V to the power of -1. That was a possibility. It looked like that, more or less. On the blog, and in follow discussions, it was told that this kind of function was generally a k over v to n, where n, the exponent, was to be determined and dependent on the type of object and dimensions of it. All right. Thinking about the simplest situation, I mean the v alone, k over v means that the actual total drag, because this is the coefficient, not drag. Drag, as you should know, the force of drag is something like half air density the CD, the drag coefficient, A, the area, the section of the object, and V squared. And this is for sure from here to there, from Mach 0 to Mach 1. That is the situation. The drag coefficient is constant and the force is proportional, depends on V squared. What happens? Well, we have a threefold increase at Mach 1, but what happens next? Well, next, in this part of this range from Mach 1 to Mach n, if this is the situation, this means that the drag coefficient is not a real coefficient. A coefficient is something which is constant, and you put it in on a formula and you can calculate something. A thing that is not constant is not properly a coefficient. But suppose we name this anyway a coefficient, but from over Mach 1 to higher velocities, the formula should change with this one being, suppose, k over v. And that means that if you put k over v here, the v of the denominator matches with the v squared, and you should get something like half density k, unknown, v squared, and you can clear 1v on each side and get something like half density Ka and V not squared. So I was figuring out, what does it mean this? Considering not this CD, the coefficient of drag, but the force drag as a whole. The force drag before Mach 1 is a parabola, is proportional to V squared. So you get a line like this, right? Then at Mach 1 you got the threefold increase. So 1, 2, 3. And what happened next? What happens next? The force should be proportional to V. proportion. It means that it is a straight line starting from the origin, and so going like this, right? Nice finding, but it's not that nice. It doesn't explain why Concorde pilots used to throttle back to switch it afterburner off after Mach 1. Maybe even after 1.5 Mach 1, but anyway, they throttle the afterburner off. It doesn't seem a situation that allows you to throttle back, because you don't have anymore the V square law, right? But you have anyway a force of drag increasing. Okay, I lived with this doubt in mind for a few weeks. Then I made a simple thing. I tried to investigate which kind of function is this. I mean, which kind of n actually is inside that formula that gives you the coefficient of drag coefficient at supersonic speed. Because maybe it's not just 1. Anyway, if it was 1, the result is incompatible with what happened with a Concorde. So let's investigate with a simple tool. You got here an example. This has been named spell diagram. Spell stands for study, or searching for study of powers, exponential, linear, or logarithmic. Spell. It's a very simple sort of sheet featuring a first part with the both axes in a linear scale. You plot here your function. For example, we got the G7 data I found on the internet. Then you have 3 more diagrams where the horizontal one or the vertical one or both of them axes are in logarithmic scale. The simplest is the one which is bilogarithmic. Both axes in logarithmic scales. It allows you to detect whether your plot is a power of n as an exponent, and it can be used. I made a video lecture of that a couple of years ago. You can put, for example, the distance of each planet from the Sun and their orbiting period. There is the third law, Kepler, saying that the relation is the t squared, the square is proportional to r to the power of 3. And putting these data on the bilogarithmic diagram, you get a straight line. And the slope of the line gets you the exponent. It's very simple. In the other two cases, logarithm and exponential, it's just a matter to have an axis with a linear scale and the other one on the logarithmic. And you can even detect this kind of behavior. For example, if you list the temperature of a glass of water, of hot water, which is decreasing in temperature over time, this kind of function is an exponential, decreasing exponential, and you put your data in this kind of semi-logarithmic. You got the linear scale on the x and the logarithmic scale on the y, on the vertical axis, and you get a straight line, showing that there's an exponential behavior. So I was using this simple sheet of paper, which is a small invention of mine. I published this kind of trick on a minor magazine for high school teachers in 1997, I guess. Now it seems a thing of the last millennium, actually, because you can do this, for example, in a spreadsheet like Excel. You got the capability to ask logarithm scales and get in a split second the diagram in such a new type of scale. But for a simple case like this, it's almost easier to do this in paper than with the technological means of this millennium. Anyway, I put these data of the decreasing part of the diagram on the bilogarithmic diagram, and I got a straight line actually. Well, the slope of this line was astonishingly different than a simple 1v to the power of 1, which was the thing I guessed at the first sight. It was something like n around 2.2, 2.1, 2.2. I tried to put these data on using Excel right now, and I get a confirmation. It's around 2.2 minus, oh sorry, minus 2.2. Minus 2.2. And this changes everything upside down. If you got a negative power, which was even -1 was a negative power, but negative power with an exponent which is more negative than the v squared here, you got a situation which is reversed. I mean, you got the force of drag here, the velocity, and here you got Mach 1. Prior to speed of sound, you got the usual parabola, v squared. Then you got the 1, 2, 3 fold increase. And after that, if the power is v to the power of 2 divided by v to the power of 2.2, you get something which is proportional to v to the power of minus O2, which is not that much, but is anyway decreasing. So you have a curve like that. Not such a slope, of course, because 0.2 is a fifth of the one you have in a normal hyperbola. But it's something that decreases, and this, on the long run, explains why the Concorde pilots used to throttle back after Mach 1, because you reach this velocity, suppose Mach 2, then you are 20% less of the maximum thrust needed when you were at Mach 1, and you can throttle back and turn the afterburner off, right? So that's all, folks. Sorry for my very slow English, but I'm getting older and older, and you know, with the average of 1 neuron lost each second, you lose a lot of neurons over the time. Listen, you get over 30 million seconds in a year. So in a year you lose almost 30 million neurons. In 10 years, in that decade, you lose 300 million neurons. And in 3 decades, almost 1 billion neurons. So I'm over 60 actually, so I've lost already almost 2 billion neurons. And so that's a result, of course. Anyway, that's enough. See you next time, if next time will take place, of course. Bye-bye.